Hello, today we are going to be doing a video about chemical kinetics, specifically radioactive decay and first-degree kinetics, and my name is Z-Sandy. So part A of this first part of this two-part question is the time for 10% decay. Question: the half-life for the radioactive decay of U-238 is 4.5 billion years and is independent of initial concentration. How many years will it take for 10% of the U-238 atoms to decay? So let's start with our knowns. We know that the half-life, or T1/2, is 4.5 times 10 to the 9 years, and 10 to the 9 is billion in scientific notation. And we know it's first-order kinetics because it's radioactive decay. Next, let's write out the half-life equation. So we know T1/2 is 0.693 over K. And I get really tripped up personally, and it's kind of easy to get tripped up if the variable you're looking for is in the denominator, so I just moved it around so it'd be K times T1/2 equals 0.693. Then we just plug and chug to find the answer, and we get that K is equal to 1.54 times 10 to the negative 10 years to the negative 1. Careful of the values because you end up dividing both sides by this value, so it's years to the negative 1. And we can assume that we start with 100% of U-238. And our equation will look like the natural log of U-238 at the time and over U-238 initial equals negative KT. So let's write out the variables again and what we know about them. So U-238T, we're saying 10% is decayed. So 100% minus 10%, 90%. And because my calculator at least doesn't have a percent button, we just turn it into a decimal. So 90% goes to 0.90. The same thing with U-238 at the beginning. And this is 100%, which again, we just turn into 1 because we want to make it a decimal for the calculator's sake. And then I just rewrote our K value, which is 1.54 times 10 to the negative 10 years to the negative 1. Then we're going to plug everything in as here. The natural log of 0.90 divided by 1.00, you want to take the natural log of the whole thing, equals negative 1.54 times 10 to the negative 10 years to the negative 1t. And then we solve it, and we get that t is 6.84 times 10 to the 8 years. So let's get started on part B. How many atoms are left? Question: if the sample initially contained 1.50 times 10 to the 18 atoms when the universe was formed 13.8 billion years ago, how many U-238 atoms does it contain now? Again, let's start with our knowns. We know that 13.8 billion years is the time we're looking for, and we're going to make this in scientific notation, which would be 1.38 times 10 to the 10 years. Notice the 10 because it's 13.8, not just 3.8, so it's an extra decimal point, a little bit more than the normal billion of 9. Then we're going to do U-238 at the initial, that's what the 0 means, and we know that it's given 1.50 times 10 to the 18 atoms, and the K, because K is a constant, is the same as the previous section, 1.54 times 10 to the negative 10 years to the negative 1. And then we use our same equation, the natural log of U-238 at the time that we're looking at, U-238 over U-238 initial equals negative KT. And here we have the equation filled out. These units will cancel, so I cross them out, and we have this. Now, once we simplify things a bit more, in order to simplify a natural log, you're going to do ln of U-238 minus ln of the denominator. This is just a log rule. Equals negative 2.1252. That's the simplified. And then I move the natural log of 1.50 times 10 to the 18 atoms to the right side, and then in order to cancel the natural log here, we do e to the ln, U-238, e to the 39.727, and then once everything's all simplified, we get that for the U-238 concentration, or it's really the amount of atoms left, but we write it the same way, equals 1.79 times 10 to the 17 atoms left. Some highlights. So we learned today that how to find the time required to reach a percent of the original concentration for radioactive decay. And concentration here also means the amount of atoms. And we used first order kinetics with associated equations like the natural log equation and what a half-life is equation with the K. That was like T1/2 equals the number over K. Found how many atoms left after a specified time period, which in our case was since the beginning of the universe, 13.8 billion years. And we also used first order kinetics with the associated equations. And thank you so much for watching, and I hope this was helpful.